Biological and physical limits to ecosystem resilience make ecosystems vulnerable to large or directional changes. So this is in many ways a theoretical construct, but it's important to think about the theory so we can begin to interpret some of the patterns that we see. Essentially, the theory is that when change exceeds ecosystem resilience, it's going to trigger that change serves as a trigger, which is going to make it more likely to shift to an alternative state. So we might have normal dynamics of an ecosystem that look like this, and then it might even be changing over time slightly but not notice it. But then when you have a disturbance that happens, that's going to lead to a categorical change in one direction or another. This is figure 12.4, which shows a couple of different factors or scenarios that are occurring that are associated with exceeding the bounds of resistance within an ecosystem. So these are, in figure 12.4, the adaptive ranges of different ecosystems relative to temporal variations in some kind of control. And so think about that as maybe temperature. On the x-axis we have time, and this is the environmental control variable, so temperature. And this gray box represents upper and lower tolerance levels. Now this is set up on an ecosystem basis, but being thought of as an individual species, and temperatures exceeding either an upper tolerance or a lower tolerance level. Once we get to the community level, and there's other factors too, you can look at the tolerance of an ecosystem process to changes in temperature, just the same as you would an individual species. So in panel A, we have an upper tolerance level and a lower tolerance level, and there's been a change that's occurring over time that's relatively gradual. So when there's a directional change, you have a certain probability initially with the variability that you have in temperature of exceeding that, but more likely over time to exceed that, at least on the upper side, because the average in that environmental variable is changing. And that's a factor that can change. It changes over time and leads to a gradual increase in the probability of exceeding a given tolerance level. And the second factor, what we have, is not necessarily a change in the mean, but an increase in the variability. So it's has relatively low variability initially, and then over time becomes more variable. And that's what they're trying to represent here. So no change in the mean, but an increase in the variability, such that over time you're more likely to exceed upper or lower tolerance limits. And then lastly, you can have the same mean and the same variability over time, and that's what's represented here. That's not necessarily changing, but you can have a reduction in the tolerance of an ecosystem to variability in the environmental control. And that's when your adaptive range declines. So we're going to talk about adaptive range. And that's what this is here, is essentially the adaptive range. And you can think about how losing individual species from an ecosystem, rare species that might turn out to be important under high temperature or low temperature, as you lose those species, the adaptive range of that ecosystem is going to decline because we don't have species that can perform well under high temperatures or low temperatures. When ecosystem resilience is exceeded, regime shifts can occur rapidly and unexpectedly. So there's a new term here, which is regime shift, which is really what that means is moving from one state to another state, and that would be considered a regime shift. And when ecosystem resilience is exceeded, that's something that can occur relatively rapidly. So there's situations where we're going to take a look at an ecosystem process over time, and everything's going to look normal, and then suddenly it's going to shift. And we're not going to be sure why that is. Why would that happen relatively rapidly and not relatively gradually? So the authors have a couple examples here. This is figure 12.5. And essentially, it can be thought of, the landscape can be thought of as going from wet to dry over time. And then this represents how stable a different state is. So in this case, think of this maybe as two different communities. When the conditions are relatively wet, the community is going to stay like this, and you might have small perturbations that roll the ball up the hill, but it's just going to roll right back down. So it's relatively stable staying here. In this case, the depth of the cup kind of defines the resilience of the ecosystem. And you can play around with the shapes in your mind, but how hard is it to move up the hill, and then how quickly would it roll back down? So there's the resistance and the recovery aspect of it. In part A, we have the response of a resilient system to a mild drought. It's steady state. It's not really going to change the system. But here in part B, we might have a massive drought, which is going to flip the system. It's going to push the ball up over the hill and back down. And we're going to be in an alternative stable state. But it also, because these two are at the same level, if it gets wet again, it could be pushed back over to this situation. In this case, the height of the hill is the same, but the depth of the valley is different. So such that once you push it to a new state, it's going to go in the new state, but it's actually going to be a lot harder to get back up the hill because the valley is deeper. And in this case, the valley is even deeper, and it's going to be even harder to push it back to its original state. So one of the examples that the authors use is cheatgrass, and this is essentially one of a non-native species in the western part of the U.S. that's taken over many of the arid grasslands. It's not considered beneficial to many degrees, but it's been relatively hard to eradicate. The phrase on this has been fire promotes cheatgrass and cheatgrass promotes fire. So before cheatgrass invasions, there tended to be grasslands with perennial bunch grasses that were relatively good for grazing. And you'd have cycles of grazing and growth and grazing and growth that kept it relatively stable. But once overgrazing occurred, that allowed cheatgrass to move in. And once that happened, we got to a situation where cheatgrass took over, and there was large amounts of cheatgrass. Once there was large amounts of cheatgrass, there was lots of fires, and those fires promoted cheatgrass. And then we got moved into an alternative stable state. To eradicate cheatgrass and push it back to the original perennial bunchgrass has been relatively hard to do. It's not been successful yet. So when we think about it in terms of adaptive landscapes, you might view it like this, that we had a system like that. There was a perturbation, which was overgrazing, plus introduction of a non-native species, which got it into a new system. So here, no fire, bunchgrass, and grazing. And then this got it into a system with fire, with cheatgrass, and probably less grazing. So that's a situation where we switched states. It was initially driven by overgrazing, for example, but reinforced by the introduction of other species and an increase in fire frequencies. So disturbances are often the trigger for regime shifts in communities facing gradual changes in conditions. So if you want to think about your condition over time, if it tends to change, that within a landscape, it might be pushing you up the hill, but then there's a disturbance that's going to really change the system and push it into a new alternative stable state. This is figure 12.6, and essentially this is what they're trying to represent for aquatic ecosystems. That over time in the aquatic ecosystem, there's two different states that you can have, a clear water state and a turbid water state, where there's a lot of plankton. And in general, you're going to have a clear water state. There might be variable whether that happens over time, but it stays in this situation. Over time, though, there's phosphorus that builds up in the sediments due to increased phosphorus inputs. And we can think of that as making the valley deeper if you ever switch over to the turbid water state. So we can add phosphorus to the system, and a lot of that phosphorus, if this is our lake, ends up being deposited in the sediments and builds up over time. Well, the phosphorus concentrations in the surface waters don't necessarily change, but they do increase in the sediments. Those two are relatively disassociated, so we can stay in the clear lake state. But if you have an extreme weather event, for example, that takes these sediments and puts them up into the water, that's going to push you over the hill and into a turbid water state. And that phosphorus can stay in that system and push the lake into being more turbid than it is clear. And that's what they have here, where you have high algal concentrations resulting from phosphorus recycling and inputs. So we're having additional inputs over time, plus a disturbance that kicks up a high phosphorus content from the sediments and maintains it high phosphorus concentrations in the surface waters and switching you over from a clear to a turbid water state.